Great. So yes, so with the discrete random variable, we can use the relative frequency distribution as the probability distribution because they share the same properties. And as we saw, when you have population data, then your relative frequency, it's no longer a theoretical probability. It really gives you the actual probability. And so that's very convenient when you have discrete random variables. But when you have continuous variables, then as you know, those two types of variables cannot be treated in the same way. And so remember, discrete variables are those variables whose value you get by counting, whereas continuous variables are those variables whose value you get by measuring. And so for continuous variables, they can take on any value within a given range as opposed to discrete variables that will take on only whole numbers or discrete values. And so you don't get decimal places with discrete variables, but with continuous variables, you do. And so the analysis has to be very different. So earlier, you would recall that we discussed the descriptive statistics measures. And so we look at specifically measures of location, like the mean, the mode, the median. And then we looked at measures of variability, like the range of the variance and the standard deviation. And so when you have very small data sets, then you know that you can calculate those values as ungroup data, and so you just take the values and you sum them up, you find the mean, and you can similarly find the standard deviation for ungroup data. However, where you have larger data sets, then you will develop your frequency distribution, and you will calculate those and you will calculate those as group data, the mean and the standard deviation specifically. You will calculate those as group data. And then, as you saw from doing your assignment, once you have your frequency distribution, you can then represent those using graphs such as histograms and frequency polygons and so on. And the histogram becomes very important here because it shows you the shape of the distribution. It shows you where the mean is. You can see where the highest frequencies are, and it shows you how spread out the values are as well. It shows you if the data is skewed in any way and in which direction it is skewed, either to the right or to the left of the mean. Just let me admit somebody in class. Great. Great. Right. And so once you've found the histogram, once you've constructed the histogram, then you can construct a polygon which sort of smooths out the curve. So the histogram is similar to your bar graphs. It has all the bars, but then you connect all the bars using your frequency polygon. And it is these sort of curves, which we call the normal distribution plot, that we use to sort of estimate probabilities for continuous random variables. So we will use these curves, and we will use some of our basic probability concepts from our last 2 or 3 classes to introduce the idea of the continuous probability distribution for discrete random variables, for continuous random variables. And we will put specific focus on the normal distribution, which has wide applications, business management research, social statistics. There's so there's so many applications for both the discrete random the probability distribution for discrete random variables as well as for continuous random variables. Some, you know, I've done research in so many areas, both related to sort of economic um, variables, economic concepts like the informal economy and survivability of small businesses, factors that influence those, as well as the prison survey, which we did. We went into all 7 prisons, we collected data, did a national study on that. We did a women's health and life experiences survey, the status of women and children in, in indigenous communities, and so many areas. So when I say it has wide application, I really mean it has wide applications. And so in your own, and I'm just saying that to bring to your attention because I know for most of you here, you will have to do a final year research, either a project or a research. And so um, just bear these in mind when thinking about what you want to study. And then you, in doing your proposal, you can then decide how you want to treat the data. So what type of data you're going to be collecting. You know you're going to be collecting some qualitative data because you're gonna ask for ethnicity, you're gonna ask for religion, you're gonna ask some other questions. But then you're also going to be collecting some quantitative data. And so some of it is going to be discrete. You're going to ask for age and that kind of thing. But then some of it is going to be continuous because you might want to know height, you might want to know weight, you might want to know some of those other measures. So um, once you've decided what type of data you're collecting, then the next question is what you're going to do with that data, how you're going to analyze that data. And so all of these concepts we're presenting or we're going through really gives you those options of what you can do based on what type of data you have. And so just bear that sort of in mind when going through this. So, so you can see how it can eventually, how it will affect you. All right, so that's a bit of a diversion. So when we have continuous variables, the calculation of the probability of values of continuous variables, it has to be.
Excuse me,
Hi,
Miss.
hi.
I think your slides it's stuck. It's not moving. We're still at the normal probability distribution. We're
Um.
still at slide 41.
Oh, okay. Not sure what is happening there. Hold on. So you still at this slide? You're still. Oh,
Yeah, we were still there.
okay, but you're seeing it moving in this view.
Well, yeah, you're at 42 now.
Okay. Just 1 second. Let me try to figure out what the matter is.
Hmm. And some persons are waiting to be let in also.
All right. So as I'm here, let me let them in. All right. This is one person.
Oh, one. Okay.
Okay. Somebody else just dropped in. Now I see it. Okay. All right. Well, let me go back to slideshow and tell me if you are seeing this same slide that I was just on with these red lines on it. So
I'm
here we
seeing slide 42.
okay. It says here we will use these curves and also some of the concepts of probability. Those are the words you're seeing on the slide that we're on.
I didn't hear you. Sorry.
Can you read the first line
Oh,
that
so it says the normal probability distribution. Here we will use these curves and also some of the concepts of probability from the previous section
great,
to
yeah,
introduce the idea of continuous probability distributions and in particular the normal distribution, which has wide applications in business and management research.
great. Thanks. Yes, that's indeed the slide we are on. So do you see when I change the slide, does it change now?
No, it is still there.
All right, I think I'll have to go through it in normal view rather than slideshow view because I'm not sure. It's probably, I don't know if it's an internet issue or if it's a computer issue on my end. So what I will try to do is just to try to, let's see if I can get this a little bigger. Right. So is that big enough? Can you see the slide?
Yes, yes, it's larger.
Okay. All right. So we'll try to work in this view because I'm not sure why it's not working in the other view. All right. So uh, what I was, I think what I was
Right, so
last
it's
saying.
moving now.
Okay, great, great. So
Mhm.
I think I heard somebody in the waiting room. This one. Oh, there's nobody there. Right. So we're gonna have to use slightly different techniques to find probabilities for continuous random variables because, as we said, those continuous variables really can take on any value on a scale or within a given range. And so, if you take, for instance, any bottle of liquid hand sanitizer, which we're all using now, if you look on the bottle, it may say, okay, 20 milliliters. But if you measure the contents in that bottle, it's not going to be exactly 20 milliliters. If you compare it with somebody else who has the same bottle that also has the same volume written on it, you're also going to get a different value. And so for things like that, there's going to be a range that the company quality assurance department deems as acceptable. And so they know that some bots are going to have more, some bots are going to have less, but there's an acceptable range. Um, and so anything outside of that range is going to be deemed unacceptable or faulty. And so people like consumer rights activists, they're usually taking samples of products, cheese, milk, all sorts of products that have weights on them to ensure that consumers are not being charged. So if they say this thing has 20 ounces, but it really has 18 or 17 ounces, and that is deemed to be unacceptable, then the company is approached to fix the issue. And so you rarely get exact measurements when you're measuring anything, and that also include when you're measuring weights and when you're measuring height. And so if you're doing a study on obesity and diabetes, for instance, you're going to have to measure um, the weight, and you're also going to have to measure the blood sugar. And so when you're measuring those things, what you absolutely do not want to do is round either the value you see on the scale or the value that you see, on the thing that you use to measure the blood sugar. You want to take that exactly as it is given. Because if you wrong, you're really going to smooth out the data, and then your variable becomes discrete because you have no decimal places, or all your decimal places are zero point 0.5. You take zero point 0.5, you round it up to the nearest zero point 0.5, or you round it down to zero point 0. And that really will make your study useless because it really destroys the integrity of the data. Same thing would happen if you're measuring hypertension and you have to take um, blood pressure. You take exactly what you see. You don't wrong. Otherwise, you're going to run into some issues. And so that is why these measures were developed specifically for a continuous variable because we know that it's not going to look the same. The values that you get, they're not going to look the same as the values that you get when you are using a discrete variable or when you're doing analysis for discrete variables. So it's slightly different, but nonetheless very useful. So we introduced the concept of the normal probability distribution. This is the most commonly used probability distribution for discrete random variables. And so, excuse me, um, uh, to introduce this concept, let's say we look at the probability of occurrence of a road accident during the course of a day. Now, accidents will occur throughout the day. They generally will peak, as you would expect, during rush hours. So when you're going to work and when you're going home, everybody else is also going to work and also going home. And so typically, you will find that at some point in your commute, you will run into either a fender bender or a serious accident. Somebody pull over because you know there's an accident, but you would expect that it would peak during rush hour. It would be therefore be impossible to group accidents by each second of the day, and so usually we take them by hours. And so we'll say, okay, we'll divide the day into hours, and then we'll see at which point or during which hours you will get the most accidents and how it's distributed. And so given that we're going to use small intervals, and so either 1 hour or 30 minutes or something, we will have an observed frequency distribution with large frequencies in some intervals and small frequencies in others. And so having this distribution, we can then plot a curve so we can see how it moves throughout the day. We can see how the frequency of road accidents vary at different hours, at every hour, and where you see the highest peak at what hour or at what hours, because we could have, as we discussed earlier in the course, you could have more than one mode in your data. So you could have two highest points at the same time. And so from looking at the shape of this curve and the value of the statistics we calculate, and so this would include the mean. So you want to know where the center of the data is. You would also, for completeness, find the median and the mode, and then of course the standard deviation. And so in this normal distribution, the two parameters that are important are the mean and the standard deviation, as for most other data sets. But those are the two parameters that we would use to find our probability or to calculate our probability. And so we look at curve, we look at the shape, and then we look at the curve, the shape and parameters of which appear to fit the population from which the sample has come. Now, what this is really saying is that each continuous variable will have its own curve and its own with its own mean and its own standard deviation. And so given that, it would be quite difficult for us to develop a probability distribution accurately or easily for each specific continuous random variable. And so the normal probability distribution allows us to use this sort of theoretical frequency distribution and apply it to our data. So our variable is going to have its own mean and its own standard deviation, but yet we can use this normal probability distribution, or as we'll see in a few minutes, the standard normal probability distribution to find our probabilities. And we will see it's a process of conversion that we will use, convert our x values from our distribution to z values for the normal distribution. Now, the most important kind of frequency distribution is one that is unimodal, meaning that it has one mode, and most of the frequencies tend to center in the middle of the data, and it sort of tails off at the end. And so this is what we would call a perfect curve. So if you plot your data and it comes out with one mode, you see one peak, and then it peaks right there in the center, and then it just tails off at the end, that is perfection. It rarely ever happens, but most times you will come close to it because most variables are at least approximately normally distributed. And so when you plot your histogram, you'll get something close to a normal curve. And if you are, for instance, using SPSS or SAT or one of the other statistical analysis software, it will allow you to plot a normal curve on your data. So you will see how far it varies from that sort of ideal data distribution shape. And so an example here, so if you consider coin tossing trial, but instead of constructing the sort of, remember we said that we can use the Venn diagram, and I think we saw in the last class how we can use the Venn diagram to represent our sample space and so on. Instead of doing that, let's take a discrete variable x as the number of heads occurring at each toss. So we're really only concerned with the number of heads. Just forget about how much heads, how much tails. We're only concerned with how many heads will occur at each trial. So if we toss the coin one time, then we know that either we can get one head, because we're only concerned with head. So we can get one head, but if it lands on a tail, then that is equivalent, or that's the same as saying we get no head. So we can get either 0 or 1. If we toss the coin 2 times, then we can get no head, because both times it could land on a tail. We could get 1 head if it lands on the head 1 time, or we can get 2 heads if it lands on the head both times. And we can continue in like manner. If we toss the coin a third time, the most we can get is 3 heads, because there will be 1 time when it lands on the head all 3 times. And we can get 2, we can get 1, we can get 0. This one. Right. Now, we're gonna see a graph next, which shows us the relative frequency histogram and polygon for 10 tosses of such a coin. Both of the histogram and the polygon, they're symmetrical. So this is one of the features of this normal distribution. So what we were trying to explain earlier with the one mode, and most of the data in the center, and the tail ends is having the values. That's what you call a symmetrical curve, because you can cut it in half and both sides will look the same way. And so this is really what we're talking about here. And so 5 is the mean, it's also the median, and it's also the mode. Most of the data, the data is moving towards the center. Most of the data clusters towards the center, and then you see the frequency values for these two are sort of tailing off. Yeah, so this is what we call, I mean, if you collect data from the field and you plot your histogram and you plot your polygon, and it looks like this, you know, this is really where you want to be as a researcher. And so the histogram, of course, is the one with the bars, and the polygon is what we get when we join all the midpoints, because remember, we plot the histogram using the frequencies. And then for each class, you will calculate a midpoint. So you can either you can use the midpoint that you calculated, or you can find the center of each bar and you join those and you get your polygon. So when you take away the bars, what you're left with is the polygon, which shows you the shape of the distribution. Unbiasedly shows you the shape of that distribution. And so this distribution is looking at the number of heads that you get in a coin toss. And so it's just here for demonstration purposes to see what a normal distribution curve would look like. If you take away these bars, what you left with is a polygon, and that really becomes a curve that we can then use later on. Similarly, for a continuous variable, we can plot a similar curve and find our, use that to start finding our probability. So if we look at the graph, again, we will see that if we take the width of each of the bar of the histogram as one unit, the area of the bar for each value is the relative frequency of that value. And the sum of the relative frequencies we know is 1. So it's plotted as the using the relative frequency distribution, and we've seen before how the relative frequency distribution is a probability distribution, and it centers around the value of the values that the variable x can assume. And so if you take away all of the bars, what you'll be left with is a curve that looks like that. And that really is your typically what a normal distribution curve would look like. And so right. And so a curve that looks like that is unimodal, has one mode, it's bell-shaped. It's, like I said, this is where all researchers, statisticians, and so on really aim to be. It's of great importance in statistical work. It's called a normal distribution, or sometimes you see it referred to as a Gaussian distribution. It's a master scientist who developed it for examining random errors of observations in experimental work. And so when we consider the relative frequency curves of continuous variables, we will see a similar pattern in the measurement of many natural phenomena. So as I was saying earlier, most variables are normally distributions. Hello? Yeah. Age, weight, height, most of those variables, if you collect them from a big enough, somebody's mic is on. If you collect them from a big enough sample, then you will find that they are normally distributed. You will get a curve that looks like that. Yeah, you will see that you will get a curve that is normally distributed. Your sample size is big enough. So there's some properties of the normal distribution that are important for consideration. First, the curve is symmetric, as we said. It's symmetric, it has that bell shape, it has one mode. And so if you cut it in half, you will find that both sides look exactly the same. All the values of y or x, whichever letter we use to represent the variable, they're greater than 0. So generally speaking, we are looking at positive values, and they approach 0 as x approaches infinity. Pay no attention to that. All you need to pay attention to is part all of the values are greater than 0. It can be proved also that the area between the curve and the x-axis is 1 unit. And so what this means is that the same for all other probability distributions, the sum of all the probabilities will be equal to 1. The mean, the mode, and the median are all the same because it's a symmetric bell-shaped distribution. They're all the same and they're equal to mu because we use parameter values for the normal distribution and not sample statistics. And so the standard deviation is also equal to sigma. So as I was saying earlier, the mean and the standard deviation are the two most important variables, or you want to call them parameters, for this distribution. And so we don't use x bar and we don't use x for this distribution. We use sigma and mu. So the mean and the standard deviation. So remember your symbols. And so um, each continuous variable will have its own curve with its own mean and its own standard deviation. And so you can plot such a curve for every variable. But the standard normal distribution has been developed to allow us to convert all of those individual distributions to a standard distribution and use a standardized value called the Z value to find probabilities for any given random variable that we're collecting data for. And so for the standard normal distribution, for any curve that you have, any variable that you have, these things on this slide are all, they have all been proven. So as you can see there, about 68% of the distribution lies within one standard deviation of the mean. So that means to say within one standard deviation of the mean means the mean plus or minus one standard deviation. So within one standard deviation means one standard deviation above the mean as well as one standard deviation below the mean. And similarly, within two standard deviations, you will find about 95% of the data, and then about 99% lies within 2.5 standard deviations of the mean. And so that means to say, when we're calculating Z values really is measured in standard deviations away from the mean. You rarely ever get a Z value that's greater than 3 because within 2.5 standard deviations of the mean, you will find 99% of your data. And so that is, these here become very important because they will guide you also when you're doing your calculations. So this presentation has already been uploaded. So you make note of this and keep it at hand. Right. So as I was just saying, the mean and standard deviation are the parameters of the normal distribution. And so those are the two variables that those are the two values that we're interested in. Given the values of these two parameters, we can find the area under the normal distribution curve for any interval. Hold on. Right. So we can find the area, we can find the value for the probability distribution for any area under the curve using the mean and the standard deviation. So there, like I said, every normal distribution, every continuous variable has its own normal distribution with its own mean and its own standard deviation. So there isn't just one normal standard deviation. There's a family of normal distribution curves for each variable, each with its own mu and its own sigma. However, what you will find identical in all of those distributions is that the mean lies at the center of the distribution. You will find that it cuts the data exactly in half, and so the two halves of the curve are exactly identical. The value of sigma, as always, gives the spread of the normal distribution curve. So the mean lies in the center, and the standard deviation will tell you how this spreads the values as. Of course, the bigger the value of your standard deviation, it tells you the more widely spread out the values in the distribution are. And so the standard normal distribution is a special case of the normal distribution. For this distribution, the value of the mean is equal to 0, and the value of the standard deviation is equal to 1. So the standard normal distribution is a standard deviation, is a standard distribution, a special distribution. The mean is always equal to 0, and the standard deviation is always equal to 1. The random variable that possesses the standard normal distribution is denoted by Z. Our variable, our random variable that we are investigating is equal to X. So we will have to convert our X values to Z values, and then we can use the standard normal distribution curve to find our probability distribution, to find our probability values. And so finding the probability for the continuous random variable, it requires us a bit more work than for the discrete random variable. And so we will now talk about z-scores, but my computer battery is running low, so let me just plug in and then I'll continue. Right, so I'm back. So Z values are Z scores. These are really what we're going to be calculating for the normal distribution. And then we can use those Z values, because those Z values really tell us how many standard deviations away from the mean our X variable, our X value lies. And so once we have that, we can then find the probability. So it really hinges on the standard deviations away from the mean. Really and truly, what we're interested in is how many standard deviations away from the mean is any given X value. So if we're in any given question, person to ask themselves how far away from the mean in terms of standard deviation, that now becomes a unit of measurement. And once we know that, we can then find the probability value. And so, as an example, so usually, like I said, the Z values are given in terms of standard deviations. And so, a Z value of 1.95 really is equivalent to 1.95 really is interpreted as 1.95 or almost 2 standard deviations away from the mean. And similarly, so signs here are important, but signs are only important to the extent that they tell us what direction we're supposed to be looking in, or where on the curve. So a value of Z negative 2.17 means that it's 2.17 standard deviations away from the mean, but it's on the left side of the mean. A positive values are on the right side of the mean, whereas negative values are on the left side of the mean. And so in finding any area on the normal distribution curve, we first have to see what sign is in front of the value. And then that tells us how far, first of all, what side of the curve we're looking at, and then how far away. So 1.95 standard deviation. Um, so we have to find that area and then the other area from 0 to um, negative 2.17. And then this is asking us for it to the left of 1.95, and this is from 0 to 2.17. So we said that the mean of the standard normal distribution is 0, and so 0 is always in the center of the data. And so what we're asking for here is the area between the center and negative 2.17. So that is to the left of the mean. And here, the value is a positive 1.95. That is to the right of the mean. And so we want the area to the left of that. If we go back to the curve that we have here, this is this is a standard normal distribution curve. The mean is 0. And then all of the positive values are on the right of that curve. All the negative values are on the left of that curve. And so if you're looking for the area between 0 and 2.17, negative 2.17, negative 2.17 will be somewhere between negative 2 and negative 2.5. And so you would shade this area. Slideshow view is not working, so that it's handicapping me a little bit. But anyway, so you would shade the area that's the first place to start when you're doing any operation with the standard normal distribution to find probability. You first shade the area that you're interested in. So if you're looking for 0 to negative 2.17, you first of all know that you're looking to the left, because all the negative values mean in this case is that the value is less than the mean. It's 2.5 standard deviations away, but it's 2.5 standard deviations less than the mean. And a positive value means only that it is greater than the mean. And so positive 1.95 would be very close to 2, so it would be here. And if we want the area to the left of that, then it means we have to shade this entire area going back to the left. And so we would have to get very familiar with this curve, but really and truly the thing to bear in mind is that a negative Z value means that you're looking to the left. A positive Z value means that you're looking to the right. Now, we mentioned earlier that we would need to convert all the X values for our specific distribution to Z values. And how do we do that conversion? It's a very simple formula, as you see here. Z is equal to X minus mu divided by sigma. Mu is the mean of the distribution. Sigma is the standard deviation of the distribution. And X is any given value within the distribution. So to find how many standard deviations away from the mean any given value is, then we use this formula for Z. It's X minus mu divided by sigma. And that will tell us how far away from the mean in terms of standard deviation. Remember, this Z is a unit of measurement, and it's measured in standard deviation. So once we know that, then we can go to the standard normal distribution curve and say, okay, we get a value of 1.95. This value is 1.95 standard deviations greater than the mean. Knowing that is the first place to start. We go to a standard normal distribution curve, we create the area, and then we construct, and then we use that to find our probability values. Bear that in mind. Great. And so, in terms of standardizing a normal distribution, we therefore start by calculating the difference between the given x value and the mean, and then we divide the difference by the standard deviation. So it's x minus mu divided by sigma to find the difference between the value and the mean, and then you divide that by the standard deviation. So if the value of x is equal to mu, and so if the value that you're trying to find the z value for is the same value as the mean, then you would see that your formula would result in 0, because the top part will give you 0, and 0 divided by anything will give you 0. And so the mean of the standard normal distribution is 0, because 0 is exactly the same as the mean. There's no difference between that and the mean in terms of standard deviation. And so that is why the mean of your standard normal distribution is 0. Now, for convenience purposes, we will round values, z values, to 2 decimal places. And that is because the table now for these probability, we don't necessarily have to calculate a probability, so to speak. We have a normal probability table that tells us what the probabilities are. What we need to find are the z values. The z values tell us the area under the curve, and then we go to the table, find our probability, and then based on the area that you're looking for, we may need to do some addition and subtraction, but that is the most you would have to do in terms of calculation. You have a table of normal probability values. Now, like I said, the first thing you need to do is find the area under the curve you're interested in and shade that area. And so the probability that the z value selected at random will lie between 0 and z is equal to the area under the curve between 0 and z. Excuse me. And so we would need to shade that area. And similarly, the probability that z will be less than a given z value is equal to the area on the curve to the left of that z value. And so as we saw with when we look into the area to the left of 1.95, we find first 1.95 and then we shade everything to the left of it because that's what we're interested in. And on the other hand, probability that z will be greater than any z value will be equal to the area on the curve to the right of that z value. So you can first find the z value under the curve, and then depending on the area that you're interested in, you're either going to the left or to the right in terms of shading. And so the shading becomes very important because that is how you know what you are interested in. Now, how can we find the areas under the curve? Like I said earlier, you would need to find the table, which I will pull up on screen shortly, and also upload for you. So we use the standard normal probability table. It tells us the area under the curve to the right of any given z value, and because the curve is symmetric, meaning that the two sides, the two halves of the curve are exactly identical, then whatever is true on the right side is also true on the left side. And so although we're using a right side table, if you get a value of a z value of negative 1.5, then the area under the curve between 0 and that value is the same as the area between 0 and positive 1.5, because the two halves of the curve are identical. And so it is important that before we do this, we're satisfied that the shape of our distribution exactly matches the shape of the normal distribution, because it has to be a symmetric distribution. All right. So just give me a minute to pull up the normal distribution table. We can take a 5-minute break. I will pull up the normal distribution table and then we will continue. All right. I think 5 minutes are up. Okay. What time is up? All right. So this is what the standard normal distribution table looks like. Anyway, right. So this is what the standard normal distribution table looks like. Now, the values that you see in the margins, these are the values that sort of you can get for your standard normal, for your Z values. And so, for instance, the way to read the table, so the values on the inside, so these four decimal place values, so 0.0438 and so on and so on. These are all probability values that you can possibly get for an area under the curve. And so to read this curve or to get a probability distribution, to get a probability value of this curve, you need a value for your Z value, excuse me, that is given to two decimal places. And so for instance, if you get a Z value of 0.12, you will get the 0.1 from this margin going down the side, and you will get the 2 from the margin at the top. So 0.12 will be that value when so you're coming across here and you're coming down here. So 0.12. So the probability there for that area under the curve will be 0.0478. If similarly you get a value of 1.05, 1.05, you will get the 1.0 in this margin again coming down to the side, and you will get the 0.05 from coming down the margin across the top. And so the value there, where the two intersect, will be 0.3531. And similarly for any Z value, that's why we round to two decimal places, 1.12, you get the 1.1 here, you get the 0.02 here. So the probability value there will be 0.386. And so, as we said, most of your values will be captured within 2.5 standard deviations of the mean. And so your table goes up to 3.0 and really 3.09. So come across here at the top, you will get the 0.09. And so you would not likely to get a Z value that is greater than that, because there are really no values that are more than 3 standard deviations above or below the mean. Remember when we say within 1 or 2 or 3 standard deviations, we mean plus and minus the mean. And so the way the table is constructed, it tells you the probability for the area under the curve between 0 and any given Z value. And so between 0 and 1, this is the area under the curve we will shade, for instance. And the probability for that area, which is if it's exactly 1.00, is going to be 0.3413. If it's a positive one, or if it's a negative one, it's the same value, because whatever is true on this side of the curve is also true on the other side. It's a symmetric curve, it's bell-shaped. Both sides of the curve are identical. So whatever is true on one side is true also on the other side. And so it means to say if we're looking for an area under the curve that is exactly between 0 and Z, we can take the area that we get, we can take the probability that we get from this table, and we don't have to do anything else with it, because the table tells you the area under the curve between 0 and that Z value. If it is, we had an example earlier where we wanted to find the area under the curve between to the left of 1.95. And so if 1.95 is definitely on the right of the curve, and so we want the area under the curve to the left of 1.95. Now, two other things I will point out about this curve. Remember, it's a probability distribution, and so the entire area under the curve is equal to 1, which means that the area under any half of this curve is equal to 0.5. 0.5 plus 0.5 is equal to 1. And so if you're looking for the area under the curve to the left of a z value, but that z value is on the right of the curve, then you will take what you get from the table. But remember, you're taking in the entire left of that curve, so you're taking in also this entire half, and this entire half is equal to 0.5. So you will have to take what you get from the table and add to that value 0.5. And so 1.95, for instance, if we look for 0.5 is coming down here, coming down this row. I believe this is a 0.5, so it's 0.00, 0.01, 0.02, 0.03, 0.04, 0.05. And so 1.95, the probability that z lies between 0 and 1.95 is 0.47744. Now, if we want the area to the left of 1.95, we will have to take that 0.4744, that's the value, yes, 0.4744. That's what you'll get on this side, but remember we want to the left, so we're taking the entire rest of the curve. I'm going to add that to that 0.5 because we already know this half is 0.5, and the table tells us between 0 and 1.95 is 0.4744, so we will add the 2, and that will give us the area to the left of that value. On the other hand, we had another example where we were asked, what is the probability that z lies between 0 and negative 2.17? And so we don't have, in that case, we won't have to do anything to our table value because the table will tell us exactly what is the probability that z lies between 0 and negative 2.17. So all we need to do is on our table find 2.17. So we have 2.1 here. And so this is 0.00, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07. And so the probability there is 0.4850, 0.4850. And so all you would need to do is shade that area between 0 and negative 2.17. And for this, you basically estimate. You know that this extreme value here is 3. And so 2.17 is going to be somewhere just thereabouts. And so you shade between 0 and negative 2.17. The probability is equal to 0.4850, I believe. Yes. So other things to bear in mind, remember we said half of the curve is equal to 0.5. And so if you're looking for the probability that z lies between 0 and any other value, either on the left or on the right, it's not going to exceed 0.5. If you're looking for the probability that at that z lies to the left of a value that's on this side of the curve, it will have to be greater than 0.5 because you already know that it's taken in a half of the curve that's equal to 0.5. So it's going to be 0.5 plus what you get on that side. And similarly, if you're looking for the area that the probability that z lies to the right of a value that is on the left side of the curve, then similarly, remember what's true on one side is also true on the other side. And so if you're taking in the other half of the curve, then it also has to be 0.5 plus what you get from the table. And so there's a lot of variations with the area you can be looking for under the curve. And so these little rules, and these rules you will not see in any notes or in any text, but I usually give them to you as guidance. And so you make notes when you're listening back to the recording. It will be very important to make note of these rules that I just explained, because that is really what will be your guide. That will be your roadmap in terms of how you actually find probabilities under the normal distribution curve. It starts with you first identifying what the area I'm interested in. Is it just an area that's between 0 and z? Then we have no issues. We find that um, we find that number on our table, and that's our probability. Is it taking in another half of the curve? If that is so, we also have no issue. We find what our table tells us, and we add it to 0.5. And there's some other variations that we'll see as we go through other examples, but for now, those are two that you will make note of. So I need to go back to my presentation. So I will stop sharing this screen and I will bring up back the PowerPoint. Right. So as we were saying, we use the standard normal table to find the probabilities. Those probabilities have already been calculated, have already been proven. So all we need to do is find the area under the curve, and then we apply that table to find those values. And so if we look at this example, time it takes a randomly selected job applicant to perform a certain task is normally distributed with a mean of 120 seconds and a standard deviation of 20 seconds. And so we want to find some probabilities. Having the probability that one, a randomly selected candidate will complete the task between 100 and 130 seconds is such a good example because it shows us a different variation from the one we just looked at. Secondly, that a randomly selected candidate will complete the task between 75 and 100 seconds, another good one. And then a randomly selected candidate will complete the task within 75 seconds. And of course, within 75 seconds would mean 75 seconds or less. And so let us try to work those out now. All right, good. So just picture this is your standard normal. This is the normal distribution curve for this specific distribution. It has a mean of 120 and it has a standard deviation of 20. It's measured in seconds, so 20 is a big value. And so the curve will be pretty widely spread out, but it has a mean. It's a symmetric distribution. It's bell-shaped. The two halves of the curve are completely identical. And so in the first example, we are asked to find the probability, let's go back to the question, that a randomly selected candidate will complete the task between 100 and 130 seconds. Now, these are x values. These here are x values. These values will need to then be converted to z values. And we saw earlier the formula for making that conversion. It's x minus mu divided by sigma. So our x value minus the mean value divided by the standard deviation. And so for both the 100 and the 130, which are x values, we will have to convert those to standard deviations, which is the z value. As once we know the z values, we can then go to our table, find the probability, and then that really answers the question. So for this particular distribution, you don't have a lot of complex calculations. The biggest challenge here is being able to use the table, because the table is really your Bible for the normal distribution. Once you have that and you can use it, then you have no issue. So we're converting, right? So remember, we're told that this distribution has a mean of 120 and a standard deviation of 20. So mu is 120, sigma is 20. Our formula says x minus mu divided by sigma. And so in converting these two values, it's going to be the x value. First, we start with the 100, which is the x value, minus the mean value divided by the standard deviation. So this is 100 minus 120 divided by 20. So of course, 100 minus 120 will give you a negative 20, because 100 less than 1. 120 divided by 20, that gives you a negative 1.00. And the 130 minus 120 divided by 20 gives you a positive. I think something is wrong with this calculation. Yeah. 130, right? Yes. Right. So this should really be. Well, let me, I can't edit it here. Let me go into slideshow mode so I can do it here. Right. So 130 minus 120, that will give you 10. And 10 divided by 20 will give you 0.50. So we disregard this. Yeah, right. So it's really what we're interested in is the probability. You see, this is 85, so that's why this. Anyway, get that. So what we're really interested in is the probability that x lies between 100 and 130. And we've just converted both of those values to standard Z values. So that is equal to the probability that Z, because Z is what we're going to the table to find. Take this written in terms of Z values. The Z.
Miss Smith, excuse me, you're writing on something because we ain't seen it.
I know what's happening when I go into say slideshow mode. Right. All right.
Now you're working, show up.
Right. All right. I'll just do it in a new slide so you see what I'm typing. So let's just put it out a new slide here. So we have a distribution with the mean equal to 120 and the standard deviation equal to 20. Trying to find the probability that x lies between 100 and 130. Now, that's going to be equal to a range on the Z, on the scale of Z values. But we need to first find the two Z values, so we're going to have to convert. And we know that Z is equal to mean to the X value minus the mean value divided by the standard deviation value. And so for the 100, it's going to be Z is equal to 100 minus 120 divided by 20 equal to minus 20 divided by 20, which is equal to minus 1.0. We're wrong with the two decimal places for these Z values. And for the second one, it's going to be 130 minus 120, again divided by 20, because it's always x minus mean divided by standard deviation. So really, the only value that's changing is this value that's in front, which is your x value. In this case, you're going to get a positive 10 divided by 20, which is equal to a 0.5, a positive 0.50. So then the probability that x lies between 100 and 130 is equal to the probability that Z lies between minus 1 and positive 0.5. So we're going to our table to find the probability. We're going to, if you notice, this is a different variation of the rule, because if you notice that we're looking for an area under the curve between a negative value and a positive value. So we want to know the probability that the random person selected will take between 100 and 130 seconds to complete this task. At 100 is less than our mean, and 130 is greater than our mean. And so we have to find essentially two areas under the curve. First, the area between 0 and negative 1, and the area between 0 and the positive 0.5. And so it's two areas that we'll find. And in this case, we will have to add the two Z values that we get from the table. And so when you're looking for an area on the curve, this is another rule to write, to make note of. When you're looking for an area under the curve between a negative Z value and a positive Z value, you have to add the two areas that you get from the curve, the two values that you get from the curve, because you're going to have to find a value, a probability value for the negative 1, and you're going to have to find another probability value for the positive 0.5. And so you will have to then add those two values. So if there was a way to share two screens, very helpful. But let's just bear in mind that we're going to the curve to find these two values, a 1.00 and a 0.50. Remember, the curve gives us, the table gives us all positive values, but we know that what is true on one side of the curve is also true on the other side of the curve. And so we're looking for 1.00, and then we're looking for 0.5. So right. So so make note of these probability values. The first we're looking for is 1.00, so 1.0 here and 0.0. So 1.00 is going to be 0.3413. 0.3413. So if we're looking for the area under the curve between negative 1.00, so negative 1 over here, and 0.05 is going to be not very far away. So it's kind of like an area that looks like that. If you shade it on your curve, you'll get an area that looks sort of like that. And so if you notice, they're on two different sides of the mean. So the table will tell you the area between 0 and this -1, because -1 is on the left of the curve, and the area between 0 and this +0.5, this is on the right side of the curve. So to effectively find that area, you will take both values from your table and you will add them. So for this half, this area here, the probability is right here, 1.00034113. And then for the 0.5, it's also to 0.50, which is 0.1554. And so we're going to add the 0.3413 and the 0.1554, and we're going to get our probability values. So if you have your calculator at hand, you can do that calculation. It's not 1.5554, it's 0.1915. This is the 0.5. Okay? So it's plus 0.1915 is 0.5. Yeah. So do you have an appreciation for what we do when we have an area under the curve between two values? As we said, they're on different sides of the curve. So you have a point, you have a 1 over here. So in essence, 100 seconds is one standard deviation less than the mean of 120. Standard deviation is 20. So of course, 100, which is 20 less than 120, is one standard deviation less than the mean. 130, which is 10 more than the mean, 10 is half a standard deviation. And so we get 0.5 for that Z value, which is again not surprising because our standard deviation is 20. Our mean is 120. And so 130 is 10 more than 120, which is half a standard deviation, more than the. And so our value of 0.5 again does not is that of what we would expect to find. And so because we have two different areas on two different sides of the mean, and we want the total area, we want the total probability that this person will take between 100 seconds and 130 seconds, we will have to add what we get from 0 to here and from 0 to here. So in this distribution, we're not calculating the probabilities. The probabilities are already calculated for us. What we're trying to do is find the probability based on the area under the standard normal distribution curve that we are looking for. What I will try to do for you is find a YouTube video that also explains how to read this table, so that in addition to this video that I will be uploading, you can have another video, and you have YouTube and all the other sites at your disposal. So you can also find some helpful videos on it. So again, this is kind of weird for me to see it this way, but I'm trying to explain it as clearly as I think I am, but I'm trying to get a sense of whether you're following any of what's happening. Right, so are there, in terms of, let me just go back to the slide and put in those values we just got from the table. So it's 0.3415 and 0.1915, and then we'll find the total area. So I need to, but it has a rate plan. But while I'm switching screens, please go ahead and ask your question. Right, so that will be equal to, we just got 0.3413 plus 0.1915, which is equal to When we add those two, we get 0.5323. For the probability, let's just put back the question that we're trying to answer. Probability that a randomly selected candidate will complete the task between 100 and 130 seconds is equal to probability that a randomly selected candidate will complete the task between 100 and 130 seconds is 0.5328. And we arrive at that by converting those two x values of 100 and 130 to z values. We get -1. For 100, we get +0.5. For 130, we go to our table and we recognize that given the two values, one is on the left and one is on the right, and we want the total area. So we're going to have to add the two areas, the one between 0 and -1, and the one between 0 and +0.5. We get probability values of 0.3413 and 0.1915. We add those, we get 0.56. And so that is the probability that a randomly selected candidate will complete the task between 100 and 130 seconds. Remember, the average time taken to complete the task is 120 seconds. So, questions? That means we followed everything and we followed nothing.
Miss,
Yes.
so even though it's negative, when you go on the
I lost you. Okay, I heard the first part, even though it's negative.
oh no, I was saying just when you go on the table, even though it was -1, right?
Yes.
1.00.
Yes.
You have to find the positive 1.00, but put it on the negative side of the graph.
Correct, because what is true on one side of the graph is true on the other side. So although it says -1.0, all this means is that it's on the left side, but it's the same area. If this was a positive or a -1, it's the same probability, the same distance between 0 and -1 and between 0 and +1. So even though you get negative values, you will take the positive value of the table and it will give you the same probability.
Okay.
Great. Anybody else has a question? All right, let's take the second example and then we will see if there's still questions. So the second question asks us to find the probability that a randomly selected candidate will complete the task between 75 and 100 seconds. Between 75 and 100 seconds. So this is going to require us, I'll just put this on a different, to apply a different rule, but the same table, the same set of kind of operation. So we know that we're looking for a probability, and it will be the probability that x lies between 75 and 100. We will find the z values now, and so we will know the z value equivalent, and so we have to convert these two. Let's just put back the values we have for our mean and standard deviation so that we're clear on the. So we have right. So if we're converting the 75 first, it's going to be 75 minus the 120, which is the mean, divided by the 20, which is the standard deviation. And so 75 minus 120 gives us a negative 45. And then we divide that by 20. And that gives us a negative 2.5. And then the 100, we already found the 100, but just for completeness, we do it again. So it's 100 minus 120 divided by 20. And that will give us a negative 20 divided by 20, which gives us a negative 1.00. And so we're looking for the probability now that Z lies between negative 2.25 and negative 1.10. So if you notice this time, both of the Z values are negative. Both of them are on the left side of the curve. So again, we're going to have to find two areas, but because both areas are on the same side of the curve and we want the area between the two, we're going to have to now, instead of adding, we're going to have to minus. So I'll show you why and how in 1 second. So just bear in mind the values we're going to the table looking for: negative 2.25 and negative 1.10, 1.00, negative 2.25 and negative 1.00. Right, so I will this. Apologize for this. Right. So let's take that out. So now we're looking for an area under the curve that is sort of 2.25 will be somewhere here, and then 1 will be somewhere here. Right. For you. And it's going to be a bigger area than that, but let's just use this for demonstration purpose. So they're both on the same side, and we want the area just between these two values. So what's going to happen? The table is set a certain way. The table is set to tell us the difference, the area between 0 and any given Z value. So when we go to the table and we ask for the area between 0 and we ask for 1.00, we get 0.3413, as you can see here. That is this area here, between 0 and 1. But the area that we want is between 1 and 2.25. So we will now find the area for 2.25. 2.25, this is 0, 1, 2, 3, 4, 5. So that is, I don't know if you can see, this is 2.2 here, and you go 0, 1, 2, 3, 4, 5. So 2.25, the area there is 0.4878. 0.4878. Just make a note of that. 0.4878. And so if we come back here, we see that we want this area hypothetically The table gave us a distance between 0 and 1, which is 0.3413. And then it gave us the area between 0 and the 2.25, which is 0.4878. So essentially, we need to get rid of this area here because if we count that, then we'd be counting a bigger probability than the one we're looking for. So we don't need the area between 0 and 1. What we need is the difference between this and this. So up to here is 0.3413, and up to here is 0.4878. So what we will do is minus the bigger number from the smaller number, and that will get rid of this area here that we don't want. And that will give us the probability for the area between here and here. So let me just say again that I know that this is not necessarily something that you know that everybody grasped the first time. I do get that, and so you will have the opportunity to listen over this recording several times as well as some
Miss,
other.
excuse me, we got notice of the test. We got notice of the test.
I will consider whether it needs to be on the exam. And not necessarily. You see, most times in the exam you have options, and so we will know between then and now. But I will take that under consideration. But I do need to teach it to you regardless of if I'm testing you on it or not. Right? Because you can't finish a first semester stats course without knowing, without at least being able to, know the system. So, I will take it under consideration. I'll say that, but don't stress about it too much. Right? So, but you got the gist, the general gist of what is happening with this.
Like to find to find it on the graph.
Yes.
But when you had the two negative, we got end up adding up something. There's something go off. They just me really pick it up. Me really
Okay,
pick it up. The force example.
you followed, but this one is a little bit okay. Good. No, that's understandable because this is one of the I guess a little more complex variations of the rules. So what essentially is happening? Let me just go that far. Thanks for asking that. So you're looking for the area under the curve between negative 2.25, it's going to be a little farther out, and negative 1.10, which is going to be somewhere here, right? So essentially, you want an area that is coming back somewhere like here. You're going to take out those extra parts. But something like that you're interested in, right? So what happens when we go to the table? The table gives us a value for negative 1, but that value is measuring between 0 and negative 1. And then it will give us a value for negative 2.25. So what we're saying is that if we add those two areas, we would be including this area here, which we don't want. We want just from here to here. So this time, instead of adding, we take away. So you're going to get a bigger value and a smaller value. Of course, we take away the smaller value from the bigger value because the smaller value is the area between 0 and 1. 1 is 0. This here, the probability for this area here is 0.3413. But we don't want that. We need to get rid of it. So we will take it away from what we got for 2.25, which we found to be 0.4878. So essentially, rather than adding, we will be taking away 0.3413 from 0.4878. So the first one we did was an addition. We needed to add the two areas. This one here, we will need to minus the two areas. So where the two areas are on the same side of the curve, whether they're on the negative side or the positive side, you will need to take away instead of adding. Does that make it any clearer, Gail?
Okay. So once you get once they're falling on the same side, you gotta take away. When you
Yes,
take away, you're gonna end up finding the direct area under the curve.
correct. Exactly. Correct. So that is essentially when you have the two values on both sides of the curve, you take away because you got to get rid of the excess area here that you don't want in your calculation of the probability. So once you minus, you will take out that and you will be left with just this area that you shaded. Right. So now we go back to the PowerPoint. Bear with me. And so we're going to take away, right? So it's going to be 0.4878 take away to 0.3413. And that is going to leave you with 0.4878 take away 0.3413. That is going to leave you with 0.1465. The probability that the person will complete the task between 75 and 100 seconds is 0.1465, and you can round that down for it to 0.15, but the table will give you all the probability values in, excuse me, to 4 decimal places, and you don't need to, I mean, you just take this, you just take that, so you don't necessarily need to round there. So the probability there is 0.1465. So you get a lower probability that the person will complete the task between 75 and 100 seconds. And then the last example is the last one here, which is the probability that a randomly selected person will complete the task within 75 seconds. But this one is going to be much shorter. You don't even need to go to the table because we already have the Z value for 75. So let's just take that back, remind ourselves that the mean is 120, the standard deviation is 20. And we're looking for the probability. If x is less than 75, probability instead is less than, we already found the Z value for 75, which we found it to be a negative 0.25. And so looking for the probability that Z is less than negative 2.25, or you could write that the other way around, that negative 2.25 is less than 10. Good. So let's make this. So this is 0. This is the mean of our distribution, which is 120. On the standard normal distribution, the mean is equal to 0. We found the area for 2.25 on the standard normal curve, and that turned out to be, we got a probability for negative 2.25 of 0.4878. When we go to the table, we do 2.25, we get 0.4878. So it's expected that this is here, right? And remember, if we're asking for whether the person will complete the task within 75 seconds, what we're really asking is whether the person will complete the task in less than 75 seconds. And so if we're going less than 25, this is 75, this is 2.25, which is same as 75. Let's just say it's here. If we want to know whether the person will complete the task in less than 75 seconds. Which direction you think we will be shading our graph in? Will be going to the left or will be going to the right? Less than 75 seconds.
Less than something like negative.
It's definitely negative, so we're definitely going to the left of this value. So we get 2.25 here, hypothetically, and we want everything to the left of it. And so the probability up to here is 0.4878. We found that on our table. And if we want less than, then we're going to have to do a takeaway. But remember, just stay with me, right? So remember, we said earlier that this entire half of the curve is equal to how much? The probability for the entire area under the curve is equal to 1. So the probability for any half of the curve is equal to how much?
0.5.
0.5. Good. So the entire half of this curve, this half, is equal to 0.5. Up to here is 0.4878. If we want everything less than that, then what we would do is take away this that we already know the value for from the entire area under the curve, the entire half of this curve, which is 0.5. So again, everything we're interested in is on one side of the curve. We know up to here. We want this remaining area here. And so if the whole thing is 0.5, then all we need to do is take away what we already know from the 0.5, and we will be left with what we need. Feel. Did you follow that?
Miss, you call me just now?
Yes, I just want to know if you understand what I just said.
I was up to where you were saying about take away a something from 0.5, something you were saying. The standard I get is 0.5 because we're looking at the half this less than side of the curve, right?
Correct.
Or something you said after the 0.5.
Good. So the whole area is 0.5. And we already found up to here, when we did the when we went to the curve to find the area for negative 2.25, we found it to be 0.4878. And if the entire thing is 0.5, then what we need to do is take away from that 0.5 the value that we got for 2.25, which is
So we're taking 0.48 from it.
correct. Yes, 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 correct. We take away that area because if we want what's left, then we take out what we already know, and we will be left with just this small part here that we interested in now. So the probability here would be 0.5 minus 0.4878. I'm going to give you a small value. Remember, up to 2.5 standard deviation, there's not many values that will fall outside of that. 0.4878, and you'll be left with very small value, 0.01. Right, so this will be your probability for, if you're interested in knowing the probability that a randomly selected candidate will complete the task within 75 seconds. Remember, within means less than. Less than means, and 75 is less than the mean. And so we're on the left side of the curve. And to find the area to the left of that value, we would have to take away the area between 0 and the value of negative 2.25. We found that to be 0.4878. And this entire thing is 0.5. So if you take away the 0.4878 from the 0.5, you will be left with um, this small value that we just found of 0.013.
So, Miss, which part really would have shade if you were to shade it?
You would have shaded the small area. So you find up to points. I if we see when I go into slideshow, the screen is not showing. But you find up to here and then you shade going backward. So it would have been an area that looks circle like that. You can see this cursor moving.
I see where you were showing me.
Okay, okay, great, great. Right. So just to recap, we went through an example that took us through three different variations of finding areas on the vector. The first was finding the area between 100 and 130 when we have a distribution with a mean of 120 and a standard deviation of 20. So we first convert the two x values to z values, and we found one to be -1 and one to be positive 0.5. And so when we go to our table, we find that one of this value is on the left side, this value is on the right side. We want the total area. So what we needed to do in this case was to add the two values we got off the table. So we add the 0.3413 to the 0.1915 to get that off. So this one was, not so complex because two different areas. You just add the two areas and you get the total complex. The second one needed a little bit more digesting, and so we want the area between 75 and 100. Both of those values are less than the mean, and so you get two negative values. But again, remember, negative values only means that these values are less than the mean, and in that case, you're looking on the left side of the curve. And so we get for 75 negative 2.25, and we get for -1, which we had already found. For 100, we'd already found the minus. And so in this case, because both areas are on the left side of the curve, and the table will give us a value between 0 and 2.25, and between 0 and 1, you're going to be having an additional area in there that you don't. And so to get rid of that, you minus the two probables rather than adding 2. First time you had to minus. First time you had to add the 2. The second time you had to minus the 2. And the third time you had to minus the table value from 0.5, which is the value that represents half of the curve. So what you wanted was a little piece of area on one half of the curve. The table tells you up to 0 and 2.25, and you want everything that's left after that. And so to get that, you will minus that value from the 0.5, which represents the entire half. This is as much as I will try to cover tonight. Are there any other questions? So we had some questions from Gail, which I hope that I was able to answer to your satisfaction.
I hope that if I got do it in the test, I able to answer it.
All right. Well, come to tutorial and let's work out some. Right. But yeah, it's the first time you see it, it looks intimidating. I'm not gonna lie. But with a little bit of practice, we can get there. I'll upload the videos for you, and I will see if I find anything helpful on YouTube by some other lecturer that may have a different way of explaining it. Also.
Good night, Miss. When is test?
All right, you can mute your mic. We agreed at the beginning of the class that the date that I was looking at is the graduation week, the graduation date, and so we will have it on the 29th. The 29th of March. Really bad. The 29th of March, but we will have the revision class next week, and we'll have all the other time leading up to that for answering any questions, dealing with any queries you may have. Between then and the test will be on the 29th. You'll have until the 30th to complete it.
Would it be all multiple choice or what type of the layout?
I will give you those specifics next week, but it will be mainly calculation based given what I observed from the last test. It will be mainly calculation based. Those seem to be the questions that everyone did much better at than the word question.
Okay, good evening, Miss.
Okay. All right, just give me a second. Let me just stop this recording.